All right?
Isn't it?
So,
No?
incline plane problems. Consider the situation, this block resting on that book. Clearly, the block is not sliding down that plane. That means the net force acting on that block must be 0, which means all the forces down the ramp must be balanced by forces up the ramp. So, if we consider our block resting on that inclined plane, we know the block's weight is acting vertically straight down. The normal force, as always, is perpendicular to the ramp. And in this case, we know that friction is acting up the ramp. And obviously the sum of all those forces is 0. But let's say, for example, that I asked you to find the coefficient of friction between that block and the book. How would you actually go about dealing with this problem? For inclined plane problems, we find it convenient to shift our frame of reference. Until now, we've said that this is horizontal. For an inclined plane problem, let the plane itself be our new horizontal frame of reference. In other words, this is now parallel, or in other words, horizontal to our frame of reference. This is perpendicular, and the weight itself is what is at some angle, and consequently must be broken into components. So in other words, if we visualize this as a surface, our weight is now clearly to the left and into the surface. So we now can say, and I'm just really quickly going to do some geometry. If I just extend this normal line down here, I know that's a right angle. If this angle is theta, this angle must also be theta, which tells us that this angle must be 90 minus theta, and that this angle must be theta as well. And so now, using my newly defined angle between my weight vector and the perpendicular to the surface of the plane, I can say that that weight vector, and I'll just extend this down a little bit so it's a bit more visible. Here's my weight vector. I now can say that the component of my weight perpendicular to the hill is mg cosine theta. And I likewise can say, that the component of my weight down the hill is mg sine theta. Now, that's a little geometry. You don't really need to know how to do that. Ideally, you would. But for our purposes, all that you really need to understand is that every single time an object is on an inclined plane, you know that the component of weight acting down the hill is mg sine theta, and the component of weight acting perpendicular to the hill is mg cosine theta. And then, of course, that allows you to do all sorts of interesting things. Specifically, this is the normal force, which also must be perpendicular, as you know. What's the relationship between the normal and the component of weight perpendicular to the hill? Must be identical. In other words, mg cosine theta is the normal force. Which, of course, makes sense, because I'm now standing on an inclined plane that's inclined at angle 0 degrees. Cosine of 0 is, of course, 1. And so my weight is identical at this moment to the normal force. So, mg cosine theta is always equal to the normal force, assuming that no acceleration is taking place in the vertical direction. And, moreover, I don't necessarily know which direction friction works. Friction could work up the slope or down the slope, depending what's happening. But I do know that friction is always mu times the normal force. Right? We've defined friction this way before. Friction is mu F normal. And I've just said that in this situation, where an object is sliding down a ramp or sliding up a ramp, the normal force is mg cosine theta. And so now I can say that friction can be expressed as mu mg cosine theta. So, For objects on a plane, takeaway lesson. Component of weight down the hill, mg sine theta. Friction, mu, mg cosine theta. And we're done.